Hi, everyone. Welcome to this session. We are excited to have you here. Currently, just waiting on the presenter, Luca, to come online. So bear with me. Hope everyone is having a great day. Hi, Luca. Um, can you hear me? I can. Can you hear me? No. You may have to your audio settings with your. I can hear you now. Well, I hear something now.
I can hear you now.
Okay,
Incredibly
awesome.
sorry. I thought it was UTC plus two. My God, it was a
That's
huge
okay.
mess.
Yeah, we're the session is live, so I'll skip my introductions, but everyone feel free to drop any questions. You like have 15 minutes.
Okay, let me fetch
Thank
my
you everyone for your
uh,
patience already. Bye.
slides. Oh, thank you, really. I'm mortified. So let me just grab my slides real quick. Um, hmm, Mamma mia. No, not this one. My God, I'm incredibly sorry. Hmm. Okay, let me just do this another way. Actually, Canva. Mm, PyData, this is my ticket. This is definitely not my slide. Oh my God, I need to really go freestyle with this one. The cards, this is not on Keynote. This is not on my slides. Uh, okay, so we're gonna make this incredibly speedy. Entire screen with this one. Okay, this is the wrong screen. Not the time to be a cat lover. There we go. Okay, here we are. I have an incredible story about this. Thank you very, very much for this. Incredible story for the reply. Time series forecasting, time zones are a mess, and we got real proof for that. But here at Extreme, we know a couple of things or two about this, and we're really going to speed run through this. So let me go straight to the bit. We do a lot of forecasting, and I'm incredibly excited to talk about this topic. And this summer, when foundational models became really popular, we were all wondering, and my company, whether foundational models could be actually used in production. And as well as with my colleague Gabriele, we went through the literature, and here's what we found out. Can you actually use foundational models for time series forecasting in production? What are them? And what should you do and guard yourself against when working with some of those and trying to benchmark them? And so today we're going to talk briefly about what they are, why they matter, and what capabilities do they unlock. And finally, how we are building and evaluating them. And this both covers terms of data sets as well as models. So this is fairly important. Forecasting and transformers. The first thing to get started with is the elephant in the room. Forecasts have never been proved successful so far in forecasting. We've always seen foundational models, actually in general, deep learning based models being outsmarted and outranked by traditional ARIMA and SARIMA forecasters, or even sometimes uh, models like gradient boosted trees applied to models in an autoregressive manner. So why do we see those models that are based on transformers actually being used for this kind of context? Well, it turns out that if you are an incredibly big company such as Amazon, you will, or Zalando, you will have an incredible amount of data where you can actually train foundational models on. Not actually foundational model in this case, but models that are tailored for a specific purpose, so for example, retail forecasting. And as Tim Chernikowski found out in this preprint paper that you can find linked above, uh, well, you can see that they even witnessed some kind of scaling laws. So a way where the model was basically just say picking up and actually working even with a transformer-based architecture. And so it turns out that these labs that had a huge amount of data found successful use cases for this model, for this kind of architecture, and found out, well, what if we went beyond and if we took any kind of data set that we could grab our hands on from the time series domain and trade one huge model about that? Here's what basically foundational models are. You take an arbitrarily large neural network that's transformer-based architecture, and you grab any possible time series data that you can find. You train the model on all of that, and hope in the end that this model learns how to pick up all those patterns, regardless of the domain, the frequency, the seasonality, and the skewness. And this sounds really promising, and I would actually tell you that this actually has an incredible property, which is that these foundational models aim to be zero-shot forecaster. And this means that they can actually, given any time series without any further training, they could generate a prediction for that. And this has its pros and cons, okay? And to be totally clear, I don't think this is ever going to replace training time series model from scratch. But from the perspective of a practitioner or somebody deploying a solution, this looks like an incredible tool you could have to add to your belt. Follow this reasoning. Suppose you enter a project when you need to perform some forecasting and or serve some model really fast for your clients, and you work with a domain where you get 10, 15, 20, 60 data points in total to start with, and maybe you get a bunch of data just every week or so, right? Well, you could take just that small amount of data and just use that to put in production a smaller model to begin with that uses this data not to train a further model, but just to deliver immediately predictions just as they come in with the forecasting model and use the data that you already have to start building a benchmark. This doesn't need to be the definitive solution, but it actually the first one that you can get. So this is not just about making forecasting like universal, but perhaps more accessible and even scalable, not the optimal solution in terms of accuracy, but perhaps in the context of just going to deployment. So this is a fairly good promise, but does it deliver? Does it hold up? Well, before doing that, we need to talk about the data, because the really weak point of those huge models is that we don't really know so far how much data they've been trained on and how diverse the data has been. When I was talking about these foundational models with other people, and when I was discussing this thought, they were like, yes, but in these data sets, they've all been trained using, I don't know, data from the energy domain, but not data that was trained, for example, on the health domain. So how do I know if they do reliable help me forecast, I don't know, heartbeat rates? And this is a serious question. And if we look at the open data sets that we have in terms of forecasting available data, we don't have much. There is this OG dataset, which is the Monash time series forecasting repository. This comes from the University in Australia, and by the renowned professor Bob Hindman or Robert Hindman that everybody knows, especially if you know R. And but this is fairly small because it has less than 1 billion observation. And the biggest, first really big data set that came out this year is the LOTSA data set, which somebody from Salesforce talked about yesterday, just yesterday, because we had yet another talk on foundational models for time series forecasting. And this LOTSA data set has a huge amount of data points compared to the Monash. And we now have also something smaller that came out like more behind the scenes this year, which is the time series file, which I think has some overlapping with Monash, and but still as a smaller amount of observation. And this seems like it's a lot, but if you think about what's happening with data in the NLP domain, so large language models, so we realize that this is incredibly small. When we talk about models like Llama, we're talking about 15 trillion data points. So like three orders of magnitude more than we actually have. And even these are just private data sets. But if we look at data sets in the open, we now have one open source, 5 trillion data sets to talk about text data points. So it looks like it's really hard to find an incredible amount of data to talk with in the public domain, whereas the private domain actually might tell us something different. And we're going to see that in a bit. But so on the one hand, we do not have a lot of public data to train the models from compared to LLMs. So it's really hard to make comparison in terms of how good they are doing. But also, we do not have data sets that are specifically set aside for evaluation. And this is an incredibly important topic because in the end, everyone is going to assess the quality of these models on those data sets. And it's going to be really, really hard to say whether these models work or not, just based on a pure, okay, let's look at what they benchmarked. Doing our own benchmark is really important, it's crucial, and it's kind of hard right now because we are at the infancy of this domain. And so when we do not have enough data, what do researchers come up with? And it turns out they usually find that using synthetic data is really promising. And in general, they found out this is a figure from the Chronos paper, which is a really famous foundational time series model from AWS Labs. They found out that adding synthetic data has a generally positive effect. And researchers have found out that like using 5, 10, 15, even 20% of synthetic data is useful and improves model performance. And what is this synthetic data? Well, it's really easy. It's just a way to combine patterns in the data. So take convex combination of the data or combine different patterns from, I don't know, similar simple AR processes. So really synthetic data that is generated from equation, let's just put it in this way, and add them in a random way, semi-random way. And this is useful, but raises a question: what is actually learning? What is actually learning? Actually, what is the model actually learning in this situation? Because if the model is learning synthetic data, that's not real data. Would you ever trust a model to make a forecast knowing that it was trained on randomly perturbated data? Given that you want to reliably forecast something in the healthcare domain, for example, where you might have people lives at stake. I'm sorry if I'm feeling like I'm exaggerating with this, but it's just to make sure that some domains could be covered, some domains this could work really well, but some others really do require thorough examination. And so now that we set aside with all this premise, with these 5-ish minutes, in the remaining 5-ish minutes, we're going to cover the models because they're incredibly fun to work with. There are a lot of those, okay, both from public and private labs. And I highlighted Chronos at times FM because they are, I would say, they're more diverse and the papers are really accessible. So I highly encourage you to go through, read them. They're really easy, not in a way to demean the authors, but they're really accessible. And you can find lots of information that even if you do not come from this domain, even if you're not a researcher, you will learn a lot learning from them. So please do go check them out. But you can find a lots of them that just came out this year alone. The Moira paper is also especially interesting because they use lots of data that it is anonymized from their own data, and it's also something actually forget about that. The Moira dataset is just public. There is another model that you cannot find here, which is trained by Datadog, that uses a huge amount of data that is anonymized data from their own private data. So I didn't include it in the list because even though it's a huge model, we do not have access to the data. So I consider it more of a closed model. And these two models, I'm going to talk about them very briefly just because they have an incredible infrastructure and the design and architecture is really nice and can show you an example of what is being done to train this and find the new appropriate architecture for these models. Chronos is, rather than a model, is a framework. So it is described as a way to pick um, existing transformers architecture and repurpose them to be forecasting models. So you take a model, they took two models, GPT-2 and T5, which is an encoder-decoder only, and they basically took that same architecture and did a clever pre-processing. and which is all everything boils down to you take the continuous domain of the time series and make it discrete because as they repurpose the structure of a model that is designed for language, so it is basically a discrete model, they need to find a way to turn the time series domain, which is continuous, potentially infinite, into discrete tokens. And they do this by applying mean scaling and quantizing time series into bins. So as you see here, basically if a value falls, for example, in this range, it will be placed into a continuous interval, a continuous bin. So you might have so every value that ranges from, I don't know, 0 to 5 falls into token number 0, and so on and so forth. And this is incredibly clever if you think it's really smart, if you think that this also can yield meaningful responses because like when the model spits out its output, it's just a token that gives you a probabilistic prediction interval. So if you take, I don't know, the top 80% probability of the sample distribution of the logits that gets spit out, you can also get a probabilistic prediction for free. And this requires the model to generate autoregressively every step of its way. But if you think about it, you can do this with any model for which we know that in the language domain, the architecture works. And what did they found out? Well, first of all, let's talk about the training data. They don't really use a lot of data. They only take 55 datasets from publicly known datasets, including the Monash repository, and they take 13 datasets for training only. And then 15 datasets are used for training and in-domain evaluation. And then 27 data sets alone are used just to train for out of domain. So this data wasn't seen in the um, training set. And they found out incredibly good results, especially when combined with the um, data mixing techniques. But let's talk about those after a while. And finally, look at the other contendant, which is time contendant, other candidate, which is times FM. Times FM, unlike our model, like Kronos, has a completely different architecture that is designed to work specifically with time series data. So it looks like a bit more a model for computer vision because it takes the continuous data and bins it into patches whose length is 32 data points in input and 128 in output. So basically, what it does is that it takes 32 data points as input, converts them into one patch, no mean scaling, no binning in this sense, and it outputs a prediction step that is 128 data points. And then for the rest is, let's just put it way straight for being concise, it's just a regular machine learning and transformer architecture. And then they use up to actually more than 100 billion data points, like in the order of 100 billion data points to train this model. So a lot more data than what you're using to see, including a lot of data from Wikipedia. You see here that they use an incredible amount of time steps from Wikipedia, basically number of clicks on certain pages to basically mirror and mimic what's happening with human interest over certain topics. And this is incredible because they think of synthetic data, especially the one that is generated, to be like we are trying to teach the model the grammar of time series patterns so that it learns and it can adapt and extrapolate to other contexts. And if we look at how this works in the benchmarking thing, it looks like everything is going fairly well because especially if you look at the Chronos metrics, you will find that it excels over anything else any kind of other model, especially when you consider that you can fine tune those models. And the beauty of Kronos is that being based on a transformer architecture, you can use any Hugging Face library that you would use to train LoRa models, for example, and use that for Kronos as well, which is incredibly powerful and flexible. But the point is, since we do not know how to use the data, how can we do this? It's really promising to be able to uh, have this burgeoning field, which is growing, where we are trying to find ways to standardize the data sets, get more and more of them so that everybody can train their own models. And fine tuning isn't being super developed, but it's a really promising avenue that allows you to take the smaller data points that you have and further optimize the model that by default should have decent performances. On the other hand, though, public benchmarks are incredibly hard to come by. And if you look at the benchmarks, you will find that maybe sometimes you might find that a model is trained on a data set that another model uses for evaluation. So if you try to make the comparison in terms of performance on the both of them, there will be some kind of a contamination. So building your own data set is mandatory. And evaluation right now is really hard to come by, and you need to build your own. So it's a promising avenue, but you need to do work to put it and test them for your own use case. And finally, I would like to really thank you, Gabriele, who's my colleague and helped me prepare this talk, which we're also given at other times. You can find the more extended version somewhere on the internet as well, where we discuss most of this. And I thank you very much for your patience. And if you have any question, please do not hesitate to reach out. I would love to guide you more a thorough session now that they have to rush this in 15 minutes. Thank you very much for your attention.
And thank you so much for coming, Luca, and for everyone for attending. If you have any other questions, feel free to use the PyData Discord or the lounge feature here on AirMeet, or of course, reach out using the LinkedIn platforms here. But thank you guys so much. We're going to go ahead and close out this session, but I hope you all have a great rest of your day.
Thank you very much. Ciao.